So here we have the Pulse Instruments test system running a test pattern that we call Welcome to Pulse. We're using the interface board and a small adapter PCB to connect the clock driver outputs that would normally be operating the focal plane to the preamplifier inputs, and this produces a closed loop test pattern that creates the moving pattern that you see on the screen. Here on the oscilloscope, you can see the monitor signals that come out from the digitizer box. The yellow trace is our sampling clock, and the blue trace is the video signal that we are converting. If I zoom in a little bit here, you can see one full pixel period from here to here. We have a repeating pattern in quarters. The first quarter is continuously high, second quarter is continuously low, the third quarter alternates between high and low, which is how we get the bright and dark pixels in the video image, and the fourth quarter again is constantly low. You can see here using our software that I have real-time control over the phasing of that sampling clock. For example, I can move this into the region which is constantly high, the region that is constantly low, and the region where the pixels are alternating bright and dark. And if I move into here, I can see that's about where the signal has finished settling before it starts its next transition. I can do this independently for each of the 4 channels. And I also have control over the analog pre-processing of the signal. For example, I can sweep the DC offset into negative saturation or positive saturation, and I can adjust the gain. That's at a gain of 1, and I can increase this to saturating on both sides. I'll leave that back at 1. And I can control the filtering. I have a 10 megahertz 3 dB filter on the signal right now. I can change this back to open. There's not much change on the video image, but you can see the waveform on the monitor points have some overshoot. And then I can use the 4-to-1 multiplexer at the back of the digitizer box as a switch. And I can turn on a single channel, any of the 4 channels, 2 channels, 3 channels, all 4 channels, and I can also use my focal plane definition controls to flip the image left to right, flip it vertically, rotate it 90 degrees, etc. And again, I can do all of this while the image is being acquired and while the focal plane is running. I've never seen a device that reads out this way, but if someone comes up with one, we can handle that. More commonly for an infrared device would be a situation like this, where each of the 4 channels is stitched into every 4th column. So I've removed the input to preamplifier number 4, and I'm missing pixels 4, 8, 12, 16, etc. I'll go put that back to normal. So that's how the system looks using our test pattern. Let's attach a real focal plane. So I'm going to load a test plan to run the Ulis microbolometer part. I'm going to load this pip file to set up the microbolometer part, and you can see here that I have various test plans that I can select on the left, and the contents of those test plans are displayed here. I'm going to choose the setup test. First I'm going to choose the disconnect test plan, and when I run this, it will shut off all the clocks and biases, making it safe to connect or disconnect the focal plane. I'm going to apply my wrist strap, remove this test adapter, and install the device under test. We're now ready to begin testing. I'll select the setup test plan, which contains all the settings for the biases, clock drivers, and timing files. I can have this display a setup page for the operator where I can select the output size, integration time, and the voltages for the two critical bias supplies. I'll go ahead and click OK. The focal plane is running now, and I have some uncorrected video from my focal plane. I'm going to use my histogram controls here to maximize the contrast, and you can see we are running with some very poor looking video. Of course, this is expected because the video is uncorrected from a microbolometer. One very nice feature of the pulse instrument system is that instead of viewing the video image, I can take my lens cap, cover the focal plane, and run a real-time noise plot. Now, what you're seeing on the screen is no longer the output voltage, but it's the standard deviation of the output voltage across 50 frames. And on the right side here, we have a noise distribution plot, and we can see that the average noise on the focal plane in this setup is right about 400 microvolts. So that's a pretty good result for this microbolometer. The factory test from Ulis, using their own in-house built test equipment, was about 600 microvolts. So we're doing quite a bit better than that. And I think by now, the focal plane is stabilized sufficiently to where we can do a 2-point non-uniformity correction and calibration. I'm going to skip using the programmable black body because I have a slightly faster way to do a quick demonstration. I will select the detector test and calibration test plan. This also presents dialog boxes where I can input the wafer number, die number, serial number, etc., the pixel area. Second dialog box asks how I want to test the part. I can choose to test offline using previously acquired data, or online using data that I'll acquire now. I have a choice between running a midpoint test for residual non-uniformity, and of course I can choose the two temperatures to test at and what my tolerances are for a bad pixel. I'm going to use the standard Ulis tolerances of 20% for responsivity and 50% for any delta T. Click continue. If I had a programmable black body hooked up, I would program it for T1 and acquire a data set. Instead, I'm going to use the lens cap. It's going to acquire 50 frames for calculating pixel noise. The second sample it wants is a midpoint temperature for the residual non-uniformity calculation. I'm going to use the palm of my hand for the midpoint temperature. And for the hot temperature, I'm going to provide a slightly higher temperature and collect another 50 frames. It's going to take these data sets, perform some basic calculations, and produce an output report in Excel. We have the output size, average pixel noise, average responsivity, any delta T, bad pixels, and operability. We also have fixed pattern noise, responsivity non-uniformity, residual non-uniformity, and given the bandwidth and the pixel area, we can calculate NEP and D star. Here's my bad pixel map showing each detected bad pixel and the addresses of the pixel that we will use to replace them. Now that we have calibration tables and a pixel replacement table, now we can generate fully corrected video. So that's fully corrected video in real time. We can display this as a grayscale, as a histogram, in false color. We can have multiple simultaneous displays. I can invert these, scale them up and down. I have an oscilloscope plot, or skyline plot. And you can see each pixel's value as a line graph. If I turn on the scope probe and turn off the live image, anywhere I click in the image, it will show me the corresponding pixels in the scope plot. I don't have a programmable black body here, but I do have a differential source that we built here at Pulse Instruments for demonstration purposes. And as you can see, there's a fairly high delta T between the hot section and the cold section. And we can see this. There must be some small thermal differences among the different areas here, but I can't see them on this display because of the way the display is rendered. But I could come over here to my histogram control and use this cursor to set this value to white and this value to black, and now when I scale the grayscale to those values, I can see those small thermal differences, including sort of a fingerprint on the black body. And I can see some air currents moving across the surface, and if I blow on it, and again I can see that in both false color and grayscale. Looks a little bit like Jupiter. So I'm seeing small contrast, small changes in temperature in the hot section, but I'm not seeing them in the cold section because the cold section is washed out all black. If I want to see the cold section, I can open up a second grayscale plot, a second histogram plot, and use a second set of cursors to set a black point and a white point for this grayscale. And now I can see small thermal changes in both the hot and cold sections simultaneously. One very obvious application for this type of display is for a scene with high dynamic range like this one. Another application would be for a two-color device, a two-color QUIP or two-color MCT. Now the previous test plan I ran to generate this correction table was a very simple test plan that acquired 2 or 3 data sets and did some very simple calculations. The automation features in PyDats can also be used to perform a more detailed characterization of your device's performance under a variety of operating conditions. I'm going to change the setup on the oscilloscope here so that you can see, in addition to the video signal and the sampling strobe, also the integration clock. This Ulis microbolometer has an integration time that is controlled by a pulse width on each line. I'm going to sweep that integration time from minimum to maximum, look at the difference in voltage between the cold area and the hot area, and plot the difference. I start my automated test plan. It verifies that I'm focused on the objects I want to see and asks me for the hot and cold regions of interest. So the hot area starts up at around 260, 111, and ends at approximately 350, 200. The cold area starts at approximately 5100 and ends at approximately 150, 200. When I click continue, if you watch the oscilloscope, you'll see that the pulse width controlling the integration time is increasing. We see the increasing delta V between the hot and cold regions, and you can see the display changing as long as the maximization is turned off. And while this loop is running, I can be off having a cup of coffee or annoying some grad students. So my loops are finished, and I get an output report showing the average temperature of the hot region, average temperature of the bottom region, and the plot of the difference between those two voltages. And I can regress that and show the slope. And my peak-to-peak non-uniformity is about 2%, which is pretty good for this type of device. So the timing pattern for this device is specified in the datasheet, where it shows the timing relationships between the master clock, the reset, integration clock, and also where there's data valid, and later in the datasheet we'll show you the serial command word. We can take this set of requirements and very quickly turn it into a timing pattern. Again, with the master clock, reset, integration clock, serial data. And the serial data can be shown here. Where the serial word is divided into 53 individual bits. And 16 different subwords with different lengths, different labels, and different allowable and default values. Those serial bits can be controlled in our software very simply using a graphical control that we can use to divide our pattern memory into subwords that match exactly with the requirements of the device. And these values can be programmed in binary, decimal, hexadecimal, or even with variables to permit parametric looping. Most of the calculation we perform in PyDATs is done using our graphical calculation engine, where the user can graphically insert tables of data and multiply, add, subtract, multiply, and divide. But for faster calculations, such as this live real-time non-uniformity correction or the application of a text overlay, we need to do processing faster than can be accomplished in a graphical context. So for that, we have a function, a DLL called functions.dll, for which we provide complete source code. That can be seen here, where, for example, the 2-point non-uniformity correction, the guts of it really are here in about 8 lines of code. This is a very simple 2-point linear nuke. If you wanted to perform a 3- or 4-point piecewise linear nuke or a log linear nuke, you could do that here. You don't have to write an entire DLL. Just copy and paste this function, change the name, edit 8 lines of code, recompile, and then you can use that function to run your device while still retaining all the graphical, programming, and automation features of PyDATs. Datasets that we acquire in PyDATs can be exported to still images as TIFF, JPEG, or bitmap, or multi-frame datasets can be exported to video very easily, such as this video of the official mascot of Indigo, which makes it very easy to integrate your images and results into standard test reports. Well, that's our focal plane test system. I hope you enjoyed the presentation, and please give us a call if you have any questions. Thank you.